Welcome to this revision video on the normal distribution. Now, the normal distribution is used to model continuous data, unlike the Poisson or binomial distribution, which you may be familiar with. And it's modelled with a barrel-shaped curve, which will vary depending on the spread of the data and other variables. And it's important to know the area under the graph is always equal to 1. And the graph is also symmetrical, so this side will be equal to 50% and this side will also be equal to 50%. And when solving a problem using normal distribution, we have to standardize the random variable. So we'll usually be told what the mean is or the standard deviation, and in order to use the normal distribution tables we have to standardize it. So when x is normally distributed with a mean mu and a standard deviation sigma, this can be transformed into the random variable z, which will be normally distributed with a mean 0 and a standard deviation of 1 through the use of this formula, where z is equal to our random variable minus the mean over the standard deviation. Okay, so all we're doing is just standardizing it in order to use the tables. So for example, here we can see that the probability of being less than our z value is equal to 0.9, because 90% is to the left. The table gives you the value to the left of your graph, and that's important to remember when solving these problems. So, first example, the random variable y is normally distributed with a mean of 25 and a standard deviation of 5, because remember, we are given the variance here, and the variance is equal to the standard deviation squared. So that means the standard deviation is equal to the square root of the variance. So the value we are interested in here for our formula is going to be 5. Because remember, z is equal to x minus our mean over the standard deviation. So we're going to do probability of y equals less than 20. Well, that's the same as probability of z being less than, apply our formula now, 20 minus 25 over 5. Should find that comes to minus 1. Now the probability of z being less than minus 1, what does that look like on our graph? It's going to be down here. You're interested in this probability here, because remember the tables give the values to the left on the graph. But we can't do minus values, so what do? Well, we use the fact that the graph is symmetrical, so that value there, that area of the graph, will be the same as that one. So we simply do 1, remember area under the graph is equal to 1, minus the probability of z being less than 1, sorry. So 1 minus probability of z being less than 1, find 1 on the table, 0.8413, 1 minus 0.8413, and that comes to 0.1587, and that's this area here. So we've answered the question. So I'm going to do a slightly trickier one now. Find the probability of y being between 18 and 26. So our random variable being between these two values. So probability of 18 being greater than y and y being less than 26. Apply our formula. It'll be 18 minus 25 over 5 and 26 minus our mean 25 over the standard deviation of 5. Work this out, what have we got? Minus 0.14 and 0.2. So again, draw a diagram of what's going on just to help you out. So 0.2 is going to be on the positive side and minus 1.4 around here somewhere. And it's this value, this area of the graph we're interested in. Okay, so how do we get this area here? Well, we do the value to the left of 0.2 minus the value to the left of minus 1.4. Because everything to the left of 0.2 taken away, and then you take away the value of the area left of minus 1.4 will give you just what's in the middle there, and that's what we want. So, write the probability of z being less than 0.2 minus the probability of z being less than minus 1.4. Look at our tables. What's the probability of z being less than 0.2? Well, let's have a look. 0.5793. Probability of z being less than minus 1.4. Now remember what you learnt in part A. You cannot use minus values. So we use the fact that the table is symmetrical, and we do 1 minus the probability of z being positive 1.4. So what does that come to? Well, positive 1.4 on our table is listed just here, 0.9192. 1 minus 0.9192. What does that value come to? 0.0808. So we simply just take one away from the other, 0.4985, which is the value of the area we needed. So this example is quite a difficult one, but a typical question to come up in an A-level statistics exam. So the thickness of some plastic shelving produced by a factory is normally distributed. Thickness is normally distributed. As part of the production process, the shelving is tested with two gauges. The first gauge is 7mm thick, and 98.61% of the shelving passes through this gauge. The second gauge is 5.22mm thick, and only 1.02% passes through this gauge. Find the mean and standard deviation of the thickness of the gauge. So as always, we write out our normal distribution. We don't know the mean or the standard deviation at this point. That's what we're trying to find out. And I always suggest putting the information into a graph. So as you can see here, I've drawn the distribution. I've used the information from the question. The question tells us the first gauge is 7mm thick and 98.61% passes through. So the area to the right of 7 will be 98.61, meaning the percentage to the right will be 1.39%, which we can write as 0.0139. And the probability of the thickness and the second gauge being less than 5.2 is only 1.02%. So we write that as 0.0102. So let's just write this out in our standard way. Probability of thickness being less than 5.2 is 0.0102, and the probability of the thickness being less than 7 is 1 minus 0.0139, so that would be 0.9861. Okay, so now we look at our tables. Well, we use our formula first of all. Remember, z is equal to our value minus the mean over the standard deviation. So the probability of z being less than 5.2 minus our mean over our standard deviation, and we do that for this value as well, for the 7, minus mean over standard deviation. And we have a look. Well, this value immediately is below 0.5, so we have to use the reciprocal, which would be minus 0.9898. Now if you're not sure why I'm doing that, just go through the first example again. And this one is above 0.5, so we'll leave that as 0.9861. So let's write that in there, 0.9898. So just draw you a second graph just to demonstrate what's going on here. We've remodeled this with our Z values. Remember, our Z value would be normally distributed with mean 0 and a standard deviation of 1. So we have a look at this. 0.9898, where is that on our tables? 9898, it's down here. 2.32. So that value in there must be equal to minus 2.32. So we can write 5.2 minus the mean over the standard deviation is equal to minus 2.32, which value on our table gives 0.9861. 2.2. So that value in there must be equal to 2.2. So just if you're unclear, we've remodeled this. So that value is 2.2 and that Z value is minus 2.32 with the same probabilities. Okay, so from here on it's pretty much straightforward, just solving simultaneously. We can do 5.2 minus the mean equals negative 2.32 times the standard deviation. 7 minus our mean equals 2.2 times the standard deviation. Let's put them both in terms of the mean. Mean equals 5.2 plus 2.32 times the standard deviation, and the mean is equal to 7 minus 2.2 times the standard deviation. If you put these two values equal to each other, you should find that the mean is equal to the standard deviation, is equal to 0.398 millimeters. And if we just sub that value back in to our equations, you should find the mean is equal to 6.12 millimeters.